In Chapter 5, we're going to explore the idea of a probability distribution. Even though this chapter contains 3 sections in our book, we're only going to cover the first 2 sections, introducing probability distributions and then looking at a specific type of probability distribution called the binomial probability distribution. First, we introduce the concept of a random variable and of a probability distribution. Then we'll see how we can visually represent a probability distribution by means of a probability histogram. We'll also look at how to calculate the mean, standard deviation, and variance for a probability distribution. And last, we'll look at how to determine whether certain outcomes are to be expected or whether they are so unexpected that we consider them to be significant, either low or high. First, let's talk about what a random variable is. A random variable is a variable, typically represented by the letter x, that has a single numerical value determined by chance for each outcome of a procedure. A probability distribution is a description that gives the probability for each value of the random variable. It is often expressed in the format of a table, formula, or graph. We'll talk about 2 types of random variables. The first is discrete. A discrete random variable has either a finite or a countable number of possible outcomes. By finite, we mean we can list what those values are and we can start and end that list. Countable means that the list may continue infinitely. However, the possible outcomes are listable. There's a way for us to organize the values in a list. If, however, there are an infinite number of possible outcomes and those outcomes are following some sort of continuous scale, such as a measurement scale, then we have what's called a continuous random variable. In this case, the possible outcomes are not listable. There's no way to organize the possible outcomes in a linear list. There are 3 requirements for a probability distribution. The first is that our random variable must be numerical, and the values associated with the variable correspond to outcomes that occur by chance, and therefore they're associated with probabilities. The second requirement is that the sum of all the probabilities for the possible outcomes, or the possible values of x, must be 1, representing 100%. On occasion, we might fall a little bit short of 1 or go a little bit over 1 due to some rounding errors. The third requirement is redundant because this is true for all probabilities, but the third requirement is that each individual probability must be a number between 0 and 1 inclusively. And again, this is true for all probabilities, so if we are talking about probabilities, this requirement will be met by default. Let's look at our first example. Let's consider births of babies. For this example, we're going to assume that males and females are equally likely to occur at birth. Just in the background, let's keep in mind that the chances of getting a boy versus a girl at birth are actually slightly different. The probability of getting a boy is a little higher at about 51.2%. However, we're going to consider, for the sake of this example, that the probability of getting a boy is 0.5 and that the probability of getting a girl is also 0.5. We're going to define the random variable x to denote the number of females that are born when there are 2 births. So x is counting the number of girls among 2 babies. Here we have a table summarizing the probability distribution. Let me move this out of the way for just a moment. So x is counting the number of girls in 2 births. Of course, we could have no girls, or we could have exactly 1 girl, or both of the births could result in girls. So the possible values of x are 0, 1, or 2. If you think back to some of the work we did in Chapter 4, we know that the 4 possible outcomes for 2 births is either boy then boy, or boy then girl, or girl then boy, and finally girl then girl. So of those 4 possible outcomes, one of them has no girls, right? The boy-boy combination has no girls. That's 1 out of 4 outcomes, which means that the probability of getting no girls is 1/4 or 0.25. 2 of those outcomes have exactly 1 girl, boy then girl or girl then boy. 2 out of the 4 outcomes then would give us a probability of 1/2 or 0.5 for getting exactly 1 girl. And finally, 1 out of those 4 outcomes has exactly 2 girls. That's the girl-girl combination. And that's 1 out of 4 possible outcomes, which gives us a probability of 1/4 or 0.25 for getting exactly 2 girls. Therefore, this is a probability distribution. All 3 requirements are met. The first requirement was that X is numerical, that it represents a random variable, meaning that it represents outcomes that occur by chance, and that they're associated with probabilities. The second requirement is met because the sum of these probabilities is exactly 1. And finally, as we said earlier, the third requirement will always be met by default because all of the probabilities are values between 0 and 1 inclusively. The random variable in this example is discrete because the possible values of X are finite. I can start and end the list. It has exactly 3 different possible values. Here we have the same probability distribution, but in visual form. This is what we call a probability histogram. It looks exactly like a traditional histogram where X represents the different values of X and Y represents frequencies. However, instead of counts, we have probabilities, which is the same thing as relative frequencies, but rather than expressing the relative frequencies in percentage form, we have them here in decimal form. One very small caveat is that relative frequencies are usually calculated based on carrying out a procedure and actually recording how many times certain outcomes occur. So it's based on action. Here we're basing it on theory. This is a simulation scenario, and therefore these probabilities are calculated theoretically based on the assumption that boys and girls are equally likely. Another way to calculate the probabilities in a probability distribution is by a formula, and the formula that we have here in this slide is available in your formula packet. However, for the purposes of this course, you will not need to compute the probabilities yourself. You will be working with probability distributions for which the values of the random variable X are provided to you, and also the corresponding probabilities for each of those X values will also be provided to you. Let's look at a second example. This table lists countries along with the proportion of unlicensed software based on data from Business Software Alliance. The question is, does this table describe a probability distribution? We're going to need to go through our 3 requirements. The first requirement, does our variable X represent a random variable? Meaning, are these outcomes occurring by chance? It appears here that they're treating this first column as the values of X, United States, China, India, and Russia. I see a problem. These X values are not numerical. Therefore, I think that first requirement clearly fails. This is not a numerical random variable. Therefore, this cannot represent a probability distribution. I do see a second violation. If we move on to requirement number 2, the sum of the probabilities should equal 1. Clearly, this is not the case, and so the second requirement is also unmet rather. So this is not a probability distribution. And that is what this slide clearly says, not a probability distribution. Now, let's talk about how to calculate some parameters for a probability distribution. Remember that with a probability distribution, we are talking about an entire population of interest, not results from a sample. Therefore, when we calculate mean, standard deviation, and variance, these are going to be considered parameters, population parameters, not sample statistics. You're going to see some different notation for the rest of this lesson because in chapters 3 and 4, we were talking about sample results, and therefore we used notations such as X bar for mean, S for standard deviation, and lowercase sigma for sample variance. However, in this section, because we're talking about population parameters, we're going to be using different notation, and we're going to see that, and I'll point that out as we move through the different calculations. First, let's look at how to calculate the mean for a probability distribution. Again, we have different notation. This is the Greek letter mu, denoting that this is the mean for an entire population, versus we used X bar in the past when we were talking about the mean of a sample. The formula is actually pretty straightforward. It's asking us to multiply each value of X by its corresponding probability. Once you have multiplied each X by its corresponding probability, you add those products. And that sum is going to be the mean of that probability distribution. Variance can be found with two different formulas. They yield the same results. One formula makes it a little bit easier to understand conceptually what's happening, and the other is going to make it a little bit easier to apply to manual calculations. Let's look at the first way of calculating variance. It's asking us to first find the mean of the probability distribution using the first formula. Then you're going to subtract the mean from each of those X values. Once you find those differences, you're going to square each of those differences. Once you square the differences, they will be multiplied by the corresponding probabilities. And once you have all those products, you're going to add them up. That will be your variance. For manual calculations, however, it will be a little bit less work for you to first square each of the X values. Then you're going to multiply those squares by each of the corresponding probabilities. And then you're going to add up those products. Once you add up those products, then you're going to subtract the square of the mean. We're going to show you how to use these formulas in a future example. Standard deviation, as we learned earlier, is always the square root of variance. So regardless of which of the two variance formulas you decide to use, simply taking the standard deviation of variance, simply taking the square root of the variance will yield the standard deviation. Let's talk about the concept of expected value. The expected value for a discrete random variable, x, is denoted by the capital letter E from our alphabet, and it stands for the mean value of all the outcomes. In other words, expected value is synonymous with mean. It's just another way of talking about the mean. Therefore, it can be found by following the formula for mean. All right, let's take a look at the example that we introduced earlier with having two births and having X count the number of females within those two births. We saw this probability table earlier in this lesson. If I wanted to calculate the mean of this distribution, I would follow the mean formula, which asks us to multiply each X value by its corresponding probability. So the value of 0 will be multiplied by its probability of 0.25. The value of 1 would be multiplied by its probability of 0.5. And the value 2 would be multiplied by its probability of 0.25. Next, I'm going to add those products. Once I add those products, I will have found the mean. Therefore, the mean number of girls that we expect, over 2 births is exactly 1. We expect 1 girl out of 2 births. Now I want to stop and interpret what this means. The mean number of girls is 1. I think this is where we can go back and tie that into expected value. I think the interpretation should go something like this. If we were looking at 2 births of babies repeatedly, so 2 births and 2 births again and 2 births again, we would expect that in each one of those pairs, one of the 2 babies would be a girl. So we have to think beyond just a single trial. We have to think about what if the procedure was repeated many, many times. So in other words, over 2 births, on average, we would expect to see 1 girl. All right, let's take a look at how to calculate standard deviation. Here they're using the first formula. Not sure why they chose to do the first formula on the PowerPoint, but now that we found the mean to be 1, you subtract the mean from each of those 3 original x values, square those differences, and then multiply by the corresponding probabilities. Then we add those up, and that will give us our variance. So the variance here is equal to 0.5. If you try going back and using the second variance formula, you'll find that it will be a little bit less work and you get the same result. The standard deviation, therefore, is the square root of 0.5, the square root of variance, which will give us approximately 0.7 if we go out to 1 decimal place. Again, the interpretation is that the mean number of females is 1 female over 2 births, or 1 girl over 2 births. When we're talking about the mean in examples like this, it makes more sense to use the language of expected value. Next, we're going to revisit the idea that when procedures are carried out and outcomes are recorded, there are certain outcomes that are to be expected and therefore are not surprising, but then there are other outcomes that we don't expect very often, so when they do occur, we are surprised. These surprising results are what we denote as significant results, either significantly low or significantly high. The rule of thumb that we have here in this slide is not new to us. We introduced this in an earlier chapter. Basically, it says that once we find the mean, which is also now synonymous with the expected value, that we do expect some fluctuation. We don't expect that each and every time we'll get exactly the expected value. So sometimes it'll be a little bit lower, still not surprising. Sometimes the results will be a little bit higher, still not surprising. But there comes a point where we are so far from the expected value that we start considering these results to be surprising or significant. The rule of thumb is that if we go 2 standard deviations below the mean, anything to the left of that, anything lower than that, would be considered significantly low. So that's the mean minus 2 times the standard deviation. On the other hand, values that are more than 2 standard deviations higher than the mean, those are considered to be significantly high values. So again, that's the mean plus 2 standard deviations or beyond. Let's go back to our example where we're looking at 2 births. We found that the mean number of females over 2 births is 1 and that the standard deviation is 0.7. So we're going to use this to determine which results are considered to be significantly low or significantly high. In particular, they want us to determine whether getting 2 females exactly is considered to be significantly high. So to consider values that are significantly low, we're going to subtract 2 standard deviations from the mean. That actually takes us to a negative number, right? Because the mean is 1. So if we subtract 2 times 0.7 from 1, we get a negative number. Well, it doesn't make sense to have a negative number of girls. That means that we're not going to ever have any significantly low number of girls. On the other hand, to find which values are considered to be significantly high, we're going to add 2 standard deviations to the mean. So that's 1 plus 2 times 0.7. And I think we also get a number that is outside the possible values, 2.4 females. Well, the highest number is 2. That means that there are going to be no values that would be considered significantly high. In this case, having 2 females is within the expected range and therefore not surprising. So again, the interpretation is that getting 2 females out of 2 births is not significantly high because it falls within the range of expected results. We can also talk about significant results when it comes to probabilities. If we want to find what constitutes a significantly high value for X, we need to find the probability of having a value equal to that number or higher. And if that sum is less than 0.05, then we say that that is significantly high. This is not a rigid cutoff score. However, it is one of the most commonly used thresholds. Another commonly used threshold is 0.01 if we need to be even more sure. On the other end, if we want to find values that are significantly low, we can add the probabilities of having that number or fewer. And if that sum is less than 0.05, then we say that those results are significantly low. How we interpret these probabilities is as follows. If under a given assumption, the probability of a particular outcome is very small, and yet the outcome occurs significantly less than or significantly greater than what we expect with that assumption, we conclude that our assumption is probably not correct. Here we revisit the idea of an expected value only because we're going to look at some examples that use this language, but recall that expected value is synonymous with mean. Here we have an example based on a game of chance, actually 2 different games of chance. You have $5 to place a bet in the Golden Nugget Casino in Las Vegas, and you want to apply that $5 to one of 2 games, and you're trying to decide where you have the better chances of having a stronger win. You decided that you're either going to play $5 on the roulette or you're going to play $5 at the craps table. Listen, if you're like me, you're not an expert on games of chance. However, they do give us some information to be able to compute the expected winnings for each of these 2 games. For the roulette, this is a wheel with different numbers on it that you spin. You're betting that the spinner will end on the number 7. And for the craps table, you are betting on the pass line in the dice game. So we're going to explain what each of these are so that we can determine which of the 2 bets is less risky. First, let's look at roulette. So roulette has 38 different numbers that the spinner can land on, and they're all of equal size. So the probability of ending on any one of those 38 slices is equal. If you bet $5 on the number 7, then the probability of losing the $5 is 37 out of 38 because there's only one correct slice. The probability of winning would be 1 out of 38, and in this case, the winning amount is $175. Why? Because they actually give you $180 in prize. However, you have to deduct the $5 that you spent to enter the game, which you don't get back. So your net earnings would be $175 if it lands on the number 7. So we're going to find the expected value or the expected winnings, actually the expected losing amount, if you bet $5 on the number 7 in roulette. Now let's compare this to playing at the craps table. If you bet $5 on the pass line at the craps table, which is a dice game, The probability of losing $5 is 251 over 495. And the probability of winning would be 244 out of 495. Now let's talk about what you're losing and what you're winning. If you're losing, obviously you lost the $5 that it took to play. If you win, you actually win $10, but your net earnings are $5 because you don't get back the $5 that you spent. So you can either lose $5 or earn $5 in net gains. We're also going to find the expected value for playing at the craps table. And then we're going to compare those two results to see where you should place your bet. We're going to treat this as a probability distribution. First, let's look at the roulette game. Either you win or you lose. If you were to lose, your expected winnings is actually negative $5. You're losing $5. If you win, your net gain is $175. The probability of losing is 37 out of 38. The probability of winning is 1 out of 38. If we treat this as a probability distribution and find the mean, which is the expected value, we multiply each x value by its corresponding probability, and then we add up those products. So negative 5 multiplied by 37 over 38 gives us this result. It's a negative quantity. $175 multiplied by 1 over 38 gives us a positive earning. And if we add up these two products, we see that our total expected gain, which in this case is an expected loss, is 26 cents lost. What this means is that if we were to repeatedly bet $5 at roulette, betting on the number 7, in the long run, we would expect to lose about 26 cents per game. Now let's look at what would happen if we played the $5 at the craps table. So if we were to lose at the craps table, we would lose $5, and the probability of that occurring is 251 over 495. If we were to win at the craps table, we win a net of $5, and the probability of winning is 244 over 495. We multiply each x value by its corresponding probability. We see that we have a loss and a gain possible. And if we add those two products, we see that the expected loss would be 7 cents per game. So again, the way to interpret this is that if we repeatedly bet $5 at the craps table, betting on the pass line, in the long run, we would expect to lose about 7 cents per game. So now comparing these two results, it seems that we have less to lose by playing at the craps table because we'd only be losing about 7 cents per game versus at the roulette wheel, we would be expecting to lose much more per game, 26 cents per game.